blah blah, we have these two problems. Let's begin with the first one. I have an example of an open cover with the segment 01 that we have to provide with no finite subcover. So what I'm gonna do is I'm gonna use the classic example of having the distance, except since we're dealing with segments and we need open cover. The parts of the open cover are gonna be open subsets, and to deal with that easily, we're gonna use segments for that. So what I'm gonna do is I'm gonna take this segment and then I'm gonna loop a little bit back like this to include this halving point. So what I'm gonna do is say that this cover is C. Let's say that it's a set of open sets G of I, and let's say that G of 0 is 0, and here we will have 0.9, not 9, 5, I don't know why you can write it like that. So what we're gonna do next is we're gonna say that G of I is equal to AI BI, and we're gonna say G of I plus 1 equals to, now we're gonna say BI minus, let's pick some nice number, for example 0.1, and here we're gonna have the distance, so B of I plus 1 over 2. So this should cover the number line now from 0 to 1 easily. And what we're gonna deal with next is, well, we have to show that it has no finite subcover, which really is pretty simple to show. If we're missing some random G in the middle of nowhere, so we have G of 1, G of 2, then we have G of I, and we loop like this, G of I plus 1, then we're obviously gonna be missing the chunk, because all of the segments here deal with number line past a certain point. All the segments are gonna be behind it, so no matter what, we're gonna miss out. So another case, we're missing entrance sections, so we begin with G3, for example, right? Or we end with some Gn. Well, then it's pretty evident that, again, it's easily shown that we have an entire chunk of the line missing. It's not particularly rigorous, but I conveyed the point. I don't want to prolong the video too much. Next problem. We have K as subset of R1. It consists of 0 and all the numbers of the form 1 over n, where n is a positive integer, and well, have to prove that it's compact without using Heine-Borel theorem. So what we're gonna do is we're gonna say that the open cover is C. We say that's collection of GI. So what we're gonna do next is we're gonna say that G of alpha is where the element 0 exists, because, well, again, there needs to be some G of I to contain 0, because otherwise this wouldn't be an open cover. So what we're gonna do next is actually, let's kind of denote it. it is alpha such that, okay, it is the quantifier. Now what we're gonna do is, we're gonna notice that an open set can't contain one number, because, again, an open set has all the points interior, and if it's interior point, then it's supposed to have other points in the neighborhood. So it can't be just one element. So let's say that beta not equal to 0 exists such that beta is a subset of g of alpha. Now, yes, since we have beta here, then essentially the entire chunk from 0 to beta is taken, and the only thing we have to show now is well, the lower ends. Now suppose b is equal to 1 over n0, where n0 is a natural number. Now what we have here is 1 over n0 minus 1, and so on up until 1, and this is more than countable. It is definitely finite, so essentially that does mean that this set is gonna be compact. That's it for today. Bye.